word problem that involves a system of inequalities, and we're going to use this system of inequalities in the system to be able to kind of do a little bit more analysis on the problem. So here we have a junior team and a senior team, and it looks like they're two soccer teams. They need to buy balls for their team, and game balls are $30 and practice balls are $18. For the senior team, they need more expensive game balls, so their game balls cost $40, but they can use a cheaper practice ball for $12. The junior team has a budget, so they can spend a maximum of $450, and the senior team has a budget that a little bit more, and they can spend up to $540. Okay, so we want to solve this inequality. So this is a system. We have our junior and our senior team. Okay, so our junior team, I'm just going to underline the details for the junior team. So our junior team relationship looks like this. So first of all, we're going to let x equal x equals the number of game balls, and this is not just for junior, so let y equal number of practice balls, because both teams need game and practice balls. Okay, so the junior team, and I'll do the junior team maybe in a different color here. So the junior team relationship looks like this. So we have $30 times x. Yeah, $30 is a game ball price, so $30 times the number of game balls, and the practice balls are $18 times the number of practice balls. And we have to spend less than or equal to $450. So there's our junior team relationship. For our senior team, they're going to have more expensive game balls, so it's going to be 40x, and cheaper practice balls, so 12y. They have a different budget. They can spend up to $540. So we want to solve this system of inequalities. So to solve this system of inequalities, we need to graph these. Okay, so I'm going to graph this system. There's my axes. I'm going to make this into y equals mx plus b. This one here. Although this one we can probably solve with the intercepts. Actually, let's solve this with the intercepts. So I'm going to make a table of values. When x is 0, y is going to be 450 divided by 18, so 25. They can buy 25 practice balls when they buy 0 game balls. Okay, if they buy 0 practice balls, then it's 450 divided by 30, and they can only buy 15 game balls. So our graph's going to look like this. I'm going to put 15 about here, 25 maybe about here. Okay, so that's 25, that's 15, and I know that there's my line, and I can spend up to the line, and because we can't have negative practice balls and stuff, really we're just dealing with quadrant 1. So this is our solution in quadrant 1. This is for the junior team. The senior team, when I do, I'm going to make this one y equals mx plus b, so y is less than or equal to negative 40x plus 540. And so we're going to divide by divide by 12, so negative 40 over 12x plus 540 over 12. Let's simplify that. 40, that's going to be 10 over 3. Negative 10 over 3 is my slope. And 540 divided by 12, that's equal to 45. Okay, so we can spend up to max, we can buy 45 practice balls, it looks like. Okay, ooh, it's going to be way up there. So I'm just going to draw 45 practice balls. Extend my axes here. That's going to be 45, yeah, practice balls, because y is practice balls. And then with a slope of negative 10 over 3. Okay, so it's going to have a slope kind of like this, negative 10 over 3, and it's going to look like that. Okay, and the solution to this is going to be that area there. Okay, so there's two solutions for individual solutions for those two inequalities. Now, it's not necessarily a system, although if we want them to have the same number of game balls and practice balls, that would then be this region in here, and they will be spending within their budget. Okay? Both would be spending, in fact, below their budget if they buy practice balls here. So let's analyze this problem. So it says solve the inequalities, so I've drawn the inequalities. The school wants the teams to have the exact same number of game and practice balls. Well, that involves every coordinate in this space. They have the same number of game and practice balls, and as long as they are underneath their respective lines, they are spending within their budget. Okay, so if we're on the line here, they have the same number of game and practice balls, but the junior team would be right on budget. Okay, the senior team is spending above their, well below their budget. Here, the senior team is spending up to their budget. Okay, but the junior team is still well below their budget. Okay, so the same number of game and practice balls gives them the example number of game and practice balls that'll work. So for part B, this is a solution. Maybe I'll write this out. This is a solution for part B. Okay, so all that area represents a solution for part B. And we can give any example in that area. Okay, so for example, my scale's not the greatest. So let's see here. So that's going to be, let's say there's 10 and 0 here. So I would say that 10 of each, okay, 10 balls of each, or let's say 5 of each. Okay, so let's say that's at 5 practice balls, 5 game balls. That is going to be within the inequality for both teams. Okay, so it's below the inequality for both teams. So we can substitute it into both inequalities. So if I test it in both inequalities here, 30 times 5 is 150. 18 times 5 is 90. So we've only spent $240. So the junior team is below their budget. Here we have 5 times 40 is 200. 5 times 12 is 60. So 260. So again, we're well below the budget at 5 and 5. Okay, so we want them to have the same number of game and practice balls. Both teams have the same number of game and practice balls, so not necessarily the same number of game balls and practice balls, but we want both teams to have the same number of balls. Okay, and they want to be able to spend as much money as they are allotted. They want to maximize the amount of money that they're able to spend. So to do that, we need to figure out where are both teams going to spend the most up to their maximum, but still have the same number of game and practice balls. Well, that would be represented by this point here, okay, that vertex, where those two graphs meet. This would be the maximum for both teams. Okay, because that represents the boundary up to how much they can spend, and they're both spending up to that. So in these inequality situations, the vertices actually represent what we call optimization points, and this is what they use in financial analysis. So the number of game balls and practice balls that maximize the money allotted, that would be the solution for C. Okay? And we would solve that by actually finding the intersection of those two lines. So to find the intersection of those lines, I'm going to take the junior team, 30x plus 18y, and I'm going to make it equal. So we're going to spend up to the boundary of $450. And here we're going to have 40x plus 12y equals, and we're going to make them spend up to their maximum or their boundary of $540. And then we're going to see where these are two are the same. So I'm going to multiply the green one here by 1.5 to match the y. So we get, and subtract. I'm going to subtract that. So I'm going to end up with 30 minus 40 times 1.5 is 60, so that's negative 30x. 18 minus 18y. 450 minus 540 times 1.5, so I'm going to do that on my calculator. Okay, so 540 times 1.5 is 810, so I'm just going to go 450 minus 810, and I get negative $360 there. So solving for x, I'm going to divide both sides by negative 30, and I get x equals 12. So we need both teams to buy 12 game balls. We still need to solve for y. So when I plug back in and solve for y, I'm going to have to actually work this out. So there's my x. I'm going to substitute back in to solve for y. So I get 30 times 12 plus 18y equals $450. So 18y equals $90. So y equals 5. Okay, so we're going to buy 12 game balls and 5 practice balls for both teams, and both teams would then be spending up to their limit of that they are allotted. So the junior team would spend $450 on their balls, and the senior team would end up spending $540 on their 12 game balls and 5 practice balls. So this is a kind of a more detailed analysis on a word problem, and this is how these systems can be used in what we call optimization problems when they're doing financial analysis.